Let's take a look at another graphing problem here. And for most of these graphing problems, I'm generally going to start off by looking for the x and y intercepts. Then I'll follow up with finding the critical points, and then we can find the inflection points. And then once we found all those key coordinates, then we can go ahead and sketch this graph. Okay, so in order to find the x and y intercepts, I like to start off by setting the x value to 0. So if I set x equal to 0, then I'm looking for my x-intercept here. And if I plug in 0 there, it turns out that y is also 0. So my x and y-intercept is at the coordinate 0, 0. All right, so there's my intercept. So 0, 0. And after that, let's look for our critical points here. So if I want to find my critical point, we need to find y prime, the first derivative. And I have 4x times e to the power negative x. So if I want to find this derivative, I need to use the product rule. So the derivative of 4x is going to be 4. And then I can multiply that with e to the power negative x plus 4x. And then I can multiply by the derivative of the second term here. And the derivative of e to the negative x is e to the power negative x times negative 1. Okay, and once we have that, we can go ahead and just try to simplify this. So this is 4e to the negative x. And then if I have this plus 4x and this negative 1, if I multiply that out, I get negative 4x. And then I have e to the power of negative x. And when we're finding our critical points, what we want to do is we want to take our first derivative and set that equal to 0. And then I need to find the x value so that my derivative here is going to be equal to 0. One thing that I can see right away is I have 4 times e to the power negative x, and I also have a negative 4 and e to the power of negative x over there. So what you can do over there is you can factor out the common term here. So let's go ahead and factor out the 4 e to the negative x. And if I factor that out, I get a 1. And then I also have a minus x. All right, so it's always good to factor if it's possible. In this case, we can factor and get a result there. One more thing I might want to do here is I have 4e to the power negative x. If you want to rewrite that as 4 divided by e to the x, that can help. And this will be bracket 1 minus x. And this is important because then we can kind of set up our number line here in a bit. Now, if I set this equal to 0, this expression right here in green, that will never go to 0. However, this part right here, 1 minus x, we see this quite a bit in math. If I set that equal to 0, then your x value equals to 1. All right, so this right here is a critical point. So x equals to 1 is a critical point. And what we need to determine now is whether that x equals to 1 is going to be a max or a min. So let's go ahead now, and I will draw out a number line here. And I'll put that critical point right on the number line here. And what we want to do now is we want to test these two regions, the yellow region and the blue region. And let's go ahead and find numbers in those regions and test them. So over here, maybe a good number you can try is maybe 100. If I plug in 100 over here, 1 minus 100 is going to be negative. And this expression right here is always going to be positive, so I don't need to check that. So it turns out that the blue region is going to be negative. Okay, all right, so after I test that point, after that, maybe I'll test the point 0. If I plug in 0 into the x value there, 1 minus 0 is going to be 1, and 1 is going to be positive, right? So this region right here is going to be positive. I just want to make a note that this 4 divided by e to the power of x, we don't need to test that because that will always be positive regardless of what x value you input there. Okay, so it turns out that at our critical point of 1, since the slope goes from positive to negative, we actually have so it goes from a positive slope to a negative slope. So we end up having a max here at 1, right? So when x equals to 1, we have a max. Okay, after that, let's go ahead and find the coordinate there. So we know, let me just kind of erase some of this now. And what we want to do now is let's go ahead and evaluate f of 1. So we know that x equals to 1 gives us a max. So let's go ahead and find its corresponding y value. And this turns out to be 4 times e to the power negative 1, which is really 4 over e. All right, so basically our critical point now, if I transfer to my critical point here, we know the x value was 1, and its y value is going to be 4 divided by e. And it turns out that this critical point is a max. Okay, so there's my critical point there. I'm done with that. And let's go ahead and now find our inflection points. So in order for me to find my inflection points, I need to find my second derivative here. So what I'll do here is I'll just erase this. I'll erase that. And I know that this is really my first derivative. So let's go ahead now and find my second derivative. And I can use the product rule again. So the derivative of 4e to the negative x. How do I find the derivative of that? Well, the constant here is 4. And then e to the negative x I can write out as e to the negative x times negative 1. Okay, so that's the derivative of the first term. And then we multiply this by the second term, which is 1 minus x. And then I close the bracket. Then the product rule states that I need to add, and then I will add my first term, which is 4e to the negative x. And then I take the derivative of this, my second term, and park that over here. So bracket, and the derivative of 1 minus x is going to be negative 1. Okay, so that's looking pretty good. And before we start simplifying, before we set this equal to 0, let's go ahead and simplify this. So I can multiply that out in yellow, and I can take this negative 1 and multiply that with the positive 4, right? So if I just clean this all up here, I guess we have negative 4e to the negative x, bracket 1 minus x. And then I have a plus and a minus, so that's going to be minus 4e to the negative x. Okay. All right, so we've simplify that, and obviously we're going to set that equal to 0 because we're looking for inflection points. And I would go ahead now and I would factor out the common terms there. So let's go ahead and factor out the negative 4e to the negative x. If I factor out that correctly, I guess I just have this part right here, which is 1 minus x. And then the tricky part here is over here. If I factor that out, so basically this divided by that, that should give me a plus 1. Okay, it's going to be a plus 1 on negative 1. And once again, if you're not sure if that's correct, just take this greatest common term here and just multiply with that with plus 1, and do you get negative 4e to the negative x? The answer is yes. All right, so just be careful with those negative signs. They are a little bit tricky to factor out here. And then we're going to set this equal to 0. And before I set this equal to 0, just like the previous problem, I'm going to take this expression right here, and I'm just going to rewrite that as negative 4 all over e to the positive x. And then my inside bracket will be, well, I have a 1 plus a 1, which is going to be 2 minus x. Okay. Now, if I set this equal to 0 here, technically this part here in blue, that is never equal to 0, so we can ignore that. But this part right here is really easy to set equal to 0, and that means x has to take on a value of 2. Okay, so x equals to 2 could be an inflection point. We just need to test it now, and in order to test that, I need another number line here. So I will draw a number line like that. And this is my second derivative, and on that second derivative I will put my x value of 2 on there. So this 2 goes there. And now I need to test both regions. So I have a yellow region and I also have a blue region. Okay. Before we test this, I just want people to know that this part here in the purple box, that will always be negative, regardless of what x value you plug in there. Okay. So I mean, the denominator will always be positive, but since you have a negative 4 on the numerator, that expression will always be a negative. So how does that work here? So if I take a number on the blue region, like maybe 100, and if I plug 100 over here, 2 minus 100 is going to be a negative, but once I take a negative and multiply with a negative there, I get a positive. So this whole region turns out to be positive. It's concave up in this region. Okay, and then let's try a number over here. So maybe I'll pick the number 0. If I plug in 0 over here, 2 minus 0 is going to be positive. However, a positive times a negative is going to be negative. So this whole region will be negative. Okay, and what that really means is I have an inflection point at the point x equals to 2 because it changes concavity. Okay. Okay, so let's go back to the original problem here, and let's go ahead and figure out what f of 2 is, right? So we know that there's an inflection point at x equals to 2. So if I plug that in, I get 4 times 2, and then e to the power of negative 2. And this is really 8 divided by e squared. Okay, so what that really means now is at the point 2 comma 8 over e squared, I have an inflection point. Okay, so there you go. We've kind of gathered the important facts now, and now we can kind of put this all together and create a sketch of this graph. Okay, now that we've kind of gathered all the key pieces of information, we can go ahead and construct a sketch of this graph here. So I have my both my number lines kind of posted here already, and let's go ahead and let's just start plugging the points here. So we have an intercept at the point 0, 0. So there's my x-intercept, and then I have a max. I have a max at 1, 4e. So just to kind of estimate, I'll put that over here. And then I also have an inflection point at the point 2, 8 over e squared. So maybe that inflection point will be somewhere here. So I'm just doing my best to approximate this. And then since I have a max at 1, I can just kind of maybe draw this in here. Okay, and now what we'll do now is let's do our best to kind of sketch this in now. So I guess if I had to sketch this, I guess the graph kind of looks like this. And I guess it goes like this. And if I take a look at this limit statement right here, if you do a simple limit analysis here, if I go forever to the right, it turns out that the original function just goes to 0. It converges to 0 here. So I guess the graph is kind of like behaving like this. Something like that. Okay, so let's see if this makes sense here. On my first derivative test, I know from the left-hand side of 1, I have a positive slope. So this is technically all positive. That's a positive slope. And then on the right-hand side of 1, the slope is negative. So basically, this is my best sketch of a negative slope. So it looks about right. Okay. And then if I take a look at my second derivative, which is f double prime, to the left of 2, I'm concave down. And for sure, this part right here, the graph is concave down. So that lines up really well. And then to the right-hand side of 2, I'm concave up. And this part right here, I did my best to sketch as concave up. And that does look concave up. Remember, when you're concave up, the graph kind of looks like that. This is concave up, right? And we're just trying to capture the left-hand side of the graph, which represents concave up here. So this region, I'm trying to represent that part of the concave up graph there. Okay, so this right here is a decent sketch of the problem here. And once again, I would just go ahead and find the intercepts, the critical points, the inflection points. Make sure you use your first derivative test. So here's my first derivative test right here. And then use your second derivative test to find where the graph is concave up and concave down. And then you can go ahead and sketch yourself the graph of this function here. All right, so let's take a look at the next graphing question here. And once again, I will start off by looking for the intercepts. So I like to look for the x-intercept first. So I let x be equal to 0. So this will be 0 plus 1. And ln of 1 is equal to 0. So it turns out that my x and y intercepts happen at the point 0, 0. Okay, so this will be 0, 0. All right, so that's done. And in order to find my critical points, I now need to, in order for me to find my critical points, I now need to take the first derivative. So this will be y prime equals 2. Now, if I have a ln of a function, the derivative of that will be 1 over x squared plus 1. And then using the chain rule, I can multiply by the inside. So the derivative of x squared plus 1 is 2x. Okay, so there's my derivative there, and I'm going to set that equal to 0, and I will just simplify the numerator. So I'll have the 2x on the numerator, and the denominator will be x squared plus 1. Okay, so whenever you have a fractional expression, which is 2x over x squared plus 1, when that equals to 0, this happens when the numerator equals to 0. So you can just set the numerator equal to 0 here, and that means x would equal to 0. Okay, so I have a critical point when x equals to 0, and now I need to determine whether that's a max or a min. Okay, so if I just change this back to y prime now, I can set up a horizontal number line. So this is a y prime, and I can put my critical point right on the number line, x is equal to 0, right? So this critical point, let's just put that there, and now let's apply the first derivative test. So I have two regions, one to the left is 0, and one to the right is 0. Okay, so if I go ahead and pick a number on the right-hand side, such as 100, if I plug that in over here, 2 times 100 is going to be positive, and the denominator is always positive, so this means this region should be positive. Okay, so that's step 1 of my first derivative test. And then let's pick a number to the left of 0, so maybe I can try negative 100. And if I try negative 100 over into the numerator there, 2 times negative 100 is negative, and the denominator is always negative, so that means the left-hand side of 0 is going to be negative. Okay. All right, so that's my first derivative test. So it turns out that the slope is going down, negative, then it goes to positive, so that means we have a minimum. We have a minimum when x equals to 0. All right, so that's the result of the first derivative test. Okay, so after that, I will go back to my original problem here, and I will go ahead and quickly evaluate f of 0. So when x equals to 0, I have ln of 0 plus 1, and that also gives me 0, right? So it turns out that my critical point, which is 0, also has a y value of 0, and this gives me a minimum. Okay, so at 0, 0 is acting as both an x and y intercept, and it's also acting as a critical point, which is a minimum. Okay, now let's go ahead and find our inflection point. In order to find the inflection point here, I will go ahead and take the second derivative now. So that's my first derivative. My second derivative is y double prime. And I will use the quotient rule here. So the derivative of 2x is going to be 2. And then I multiply by the denominator. So I'm using the quotient rule here. So x squared plus 1. And then the quotient rule states that I need a minus sign. And then I multiply by the numerator, which is 2x. And then I multiply by the derivative of the denominator. And the derivative of the denominator is just 2x. And then I divide by the denominator all squared. So this will be x squared plus 1 all to the power 2. Okay, so that is your second derivative there. And let's do our best to kind of just simplify this. So if I just distribute that, I get 2x squared plus 2. And then this will give me, a negative 4x squared. And if I simplify that, it turns out that 2x squared minus 4x squared, that's going to give me a negative 2x squared, right? So let me erase this, erase that. Then I get a negative 2x squared. And then we're also just dividing by the whole denominator, which is x squared plus 1 all to the power 2. And this is my second derivative. Okay. Now, in order for me to set my find my inflection points here, I need to take my second derivative and set that equal to 0. And when I'm setting my second derivative equal to 0, and since we have a fraction gain, you only care about the numerator there. So there's a few ways you can do this, but I'll factor out a 2, and I get 1 minus x squared. And from that, anyways, I'll divide that by, x squared plus 1 all to the power 2. But from here, you need to be able to look at this and know that this part right here, that goes to 0 whenever x equals, you can set that equals 0 by doing this. All right, and that means x squared equals to 1, and x would equal to plus or minus 1. Okay, so that's really important now, because when you're looking for your inflection points here, you want to set up your second derivative number line here. And you want to put your x values on that number line, which is -1 and +1. And now you want to test 3 regions here, right? So there's 2 green regions and 1 blue region there. Okay. So this is always going to take a little bit of work too when you're testing the regions. However, if I test a region over here, such as 100, if I plug that in over here, I get 2 times 1 minus 100 squared, and clearly the numerator will be negative, and the denominator is always positive. So that means that pretty much means the region on the left hand side is going to be negative. Okay, and then let's take the test point in the middle region here. Let's pick 0. And if I plug in 0 over here, 1 minus 0 is going to be positive, and a positive divided by positive means this whole region will be positive. Okay, that's for that region, and let's pick a region over here. Let's try negative 100. If I plug in negative 100 over here, I get 2 minus 100 squared. So negative 100 squared is positive, but 1 minus that will be negative. So a negative divided by a positive is going to be negative. So this whole region here is going to be negative. All right, so do take a little bit of time to test that. And then you'll notice that we go from concave down, concave up, and concave down. So this means we have an inflection point here, and we have an inflection point there because it changes concavity. Okay, so what I want to do now is I want to go back to my original function, and let's go ahead and evaluate f of 1 and f of negative 1. So both f of 1 and negative 1 both give me ln of bracket 1 plus 1, which is 2. Because negative 1 squared is 1, so 1 plus 1 is 2 again. So it turns out that my inflection points, I have one at 1 comma ln 2, and I have another one at negative 1 comma ln 2 as well. So those are my inflection points right there. Okay, so quite a bit of work there, and with that we can now sketch the graph here. And as you can see now, I have put all the key pieces of information on the side here, and I have my first derivative test up here as f prime of x, and then I have my second derivative a number line over here for concavity, and I'm pretty much ready to graph this. So here's negative 1, here's positive 1, here's my critical point is 0. Let's go ahead and graph this now. So I have a minimum at 0, 0, so let's put a 0 right there. That's 0, 0. And then I have an inflection point at 1 comma ln 2, so maybe that's somewhere over here. Sorry, let me just kind of line this up correctly here. So my 1 is there, so there's my, that right there could be my inflection point. And if I do this very carefully, somewhere over here, roughly around here, is also my inflection point. So that's negative 1 comma ln 2, and this point right. So this point right here is 1 comma ln 2, and this point right here is negative 1 ln 2, roughly. Okay, and we also have a minimum at 0, 0, right? So if I have a minimum, maybe my graph will look like that. So there's my minimum there. Okay, so now let's do our best now to sketch this. Sketching this, generally we gotta just try our best here. So I guess we need to connect the dots here. And I guess the graph is just leveling off. Something like that. So this is a decent sketch, and let's go ahead and test this now. So on my first derivative test, on the left is 0, I have a negative slope, and clearly this right here is a negative slope, so that works. And then on the right hand side of 0, the slope is positive, and this is my positive slope. So the first derivative test lines up. Okay, now let's take a look at the second derivative here. So at negative 1, I am concave down here, so maybe I could improve the concavity down here, kind of like that maybe. Oops. Okay, so this is kind of like concave down, and then in the middle here I'm concave up, so this right here looks concave up, and then I have more concave down on the, so over here I'm concave down now, so let me do my best to kind of clean this up here. Something like that. That looks like concave down. Okay. Regarding the concave down, I just want to say that most students know that concave down is roughly this shape right here, right? That's concave down. This is C down. What I'm just trying to do is I'm just trying to capture this part right here. So on the left hand side, I'm trying to capture that part right there, and then this part right here, the concave down, I'm just trying to capture that over here. Okay, so I'm trying my best to kind of sketch that image there. It may not look like that exactly, but that's what I'm just trying to do. But I'm not doing a good job sketching it. But that's what the graph should kind of look like, concave down. Okay, so that concludes this homework video guide. Hopefully you can sketch your graphs a little bit better than I can. Just check your answers using a graphing calculator, and then you should be good.